So what we have done for the previous couple of lessons is to learn about the data manipulation capabilities of R and the tidyverse. And we have seen that what makes the system very flexible is that the various facilities that are available in the tidyverse, such as selecting for different columns, filtering for different rows, such as mutating on new columns onto an existing table, and so on and so forth, that these different operations can be combined in arbitrary ways and put together as if they were Lego pieces to solve various more complicated problems. And the thing that allows one to combine these different elements like Lego pieces is that they all fit together in the sense that each of these functions take in a table as their first input and produce yet another table as their output. So that is why they can be straightforwardly chained together, and as we have seen, the piping notation really helps in doing just that. Now, in today's lesson, we're going to be learning yet another data manipulation technique, one that allows us to split up our data into separate groups and compute various quantities of interest individually on those groups themselves. So let us get going and see how that actually works in practice. So here's a very simple data set illustrating that idea. This is the whole data, so 6 rows and 3 columns. And what this documents is an imaginary measurement of the abundance of some organism of interest out in the field. So we imagine that we go out to the field on 3 subsequent days. And on each of these days, we measure the number of individuals in 2 independent locations. So as you can see, this table consists of 3 columns. The first column is the day, whether we went out to measure on day 1, day 2, or day 3. And the second column is patch, namely which of the 2 locations we've done the measurement in. Is it patch A or patch B? And then in the third column, you can see the actual number of individuals that have been measured on the given day and in the given patch. Alright, so this table is actually simple enough that we don't need to load it from a file, we can just enter it by hand. So we begin, of course, as always, by loading the tidyverse. And once we do that, we have access to our good old friend, the tibble function, which, if you remember, stands for transposed tibble, and it allows us to enter data by hand in a format that resembles the actual final output of the data. So as you can see, we define the table, which has 3 columns: day, patch, and number of individuals. And remember that you have to prepend the column names by a tilde symbol, the wiggly line, in order to indicate that those are actually column names. And underneath we can list the actual entries. And if we enter this in R and ask the computer what the value of a pop is, namely the variable to which we've assigned this table, then you can see that it is exactly as we expect. It's a tibble with 6 rows and 3 columns. The 3 columns are day, patch, and individuals, and all the entries are exactly as we have seen before. So now that we have the data in hand, let us see what we can do with it to perform summaries. So the function that we need that will perform summary computations is called summarise. So summarise, like other tidyverse functions, takes in the data as its first input, which we're going to be piping in as usual. And then its next input is as follows. We have to define a name for the new column that we're going to be creating. So in this sense, summarise begins just like the mutate function, where one has to specify the name of the new column that is going to be mutated. In this case, we're also defining a new column that is going to be created, but it is going to somehow summarize the data for us. And then, after the equality symbol, we describe how we wish to summarize the data. For example, as you can see in this table, we want to find the number of individuals that is the largest in the data set. So we define the new column, we call it max_ind for maximum number of individuals, and we literally compute it as the maximum of the entries in the ind column, which records the number of individuals. What is that entry? You can see the answer on the screen. It is 166. And notice that what we've gotten back is a tibble with one single row and one single column. The one single column is the max ind that we've defined, the maximum number of individuals, and there's only one single row which records the actual maximum number of individuals in the table. That happens to be 166. And if I just go back one step to the slide and we look at the number of individuals in that column for a moment, you see that in fact, if one looks through all those values, indeed it is 166, which happens to be the largest entry in that column. So that is why we have gotten the result that we have gotten. In fact, this is no different from simply obtaining the maximum of the vector of the number of individuals from the table pop. So remember the dollar notation. When we write down pop, which is a tibble, we can refer to one of its columns as a vector by using the dollar notation. So if we say pop dollar ind, what that means, take all the entries in the column called ind and treat them as a vector. In this case, that is a numeric vector, and we take its maximum and we get back 166, the same answer as above. So really the only difference between the form at the top and the form at the bottom is, apart from having to type a little more, is in the format of the output. Namely, in the top we get back a simple tibble, and in the bottom we just get back a single number. As another example, we could also compute the mean number of individuals, maybe slightly more useful. So we use the summarise function to define a new column called mean ind, for mean number of individuals. And then we set that equal to the average of all the entries found in the ind column. And if we do that computation, we get back the result, a tibble with just a single column, namely the one that we wanted to summarize on, and a single row, which contains the mean number of individuals. And once again, this is exactly the same as if we had entered mean of pop dollar ind, because yet again, pop dollar ind extracts the ind column as a vector, and then the mean function computes their arithmetic average. So just to take stock of where we are at, the way the summarise function works is as follows. We first define a name for an intended new column we want to create and set it equal to some function of a column or several columns if we want to, such that all the values of that column as a vector get collapsed down into a single value. So if you think about it, when we computed either the maximum or, as in this slide, the mean of the number of individuals, what we've done is we've taken the number of individuals as a vector, meaning the whole column, and then computed some function over it that returns a single number. And that single number was either the maximum of that vector, or in this case, what you can see on the slide, the average of the values in that vector. So that is the commonality in how we have to use summarise. And then importantly, all those columns that we summarize over, such as the original day and patch columns in the pop table, those get dropped. Those no longer get displayed. Since we've already averaged them over, there's no point in displaying them anymore. That is why in the resulting tibble that you can see at the top, you do not see day and patch anymore. All you see is the mean ind newly created summary column. Incidentally, as a side note, I should mention that summarise has an alternative spelling. Namely, it can be spelled with a Z like we have done so, or with an S. The two are completely equivalent. You are welcome to choose whichever spelling you prefer. And the reason I am mentioning that there is an alternative is because if you browse online or other sources, you might come across the alternative form. And if you do so, you should just be aware that no, it is not a mistake, it is not a typo, it is just an alternative spelling of the same function, and it will work just as well as the other one. Alright, so that's all well, but you might justifiably be thinking, why should I ever use summarise? After all, as we've seen, we get the same effect if we simply extract a column from a table using the dollar notation and then apply some summary function to that. So that actually works in fewer keystrokes than having to use the summarise function. Why would we ever bother with summarise? The answer to that question is that the real power of summarise comes through when applied to data that are grouped. So that's why in the next step we're going to be taking a look at data grouping. So the function that performs the grouping is called group by, as you can see on the slide. Its first input, as always, is the data, and then its subsequent inputs are the columns by which we wish to do the grouping. So as an example, let us see what happens if we group the pop dataset by the single column patch. Here is the output produced by this line. At first glance, nothing really happened. All the data seem to be identical to what we had before. But if we look carefully, we see that there's an extra line with a comment in it, namely this line. It says groups and then patch and in brackets the number 2. So what this means is that the data are grouped by patch and that there are 2 groups of data. Because the way the grouping works is that we take the column by which we grouped, and then we look for identical values in that column, and those identical values will form a group. In this particular example, rows 1, 3, and 5 all have A in the patch column, therefore they will form a group. And similarly, rows 2, 4, and 6 have the entry B in them. They are identical and therefore they will also form a different group, and those are the 2 groups into which the data are currently being split. So to be able to visualize this idea a little more transparently, let us, instead of using the console output for a table, switch back to sort of a neater spreadsheet-like display of the data. So here is our pop dataset in its full glory. And then if we apply group by patch to that, then what happens is that all of those rows that have patch A in them will form one group, and all of those rows that have patch B in them will form another group. And here I have color-coded them. The blue group is the patch A group, and the green group, those rows that are highlighted with a green color, those are the patch B group. Okay, so now we have grouped our data. What happens if we try to summarize over them? And we're going to be doing the same thing that we have been doing before, just without the grouping, namely trying to find the maximum number of individuals. So we define a new column called maxInd, and it's computed as the maximum over the column called ind, which refers to the number of individuals. So let's see how this would work. We start out with the grouped table that you can see. And then when we compute summarise, what happens internally is that this table gets split up into the 2 subtables defined by the groupings. So the first subtable consists of only the blue rows and the second subtable of only the green rows. And then we apply the summary function to each of these tables in turn. First we apply it to the blue table, and we go to the ind column for number of individuals and find the maximum there, which happens to be in row number 2, 86. Then we go on to the green table and find the maximum number of individuals in there, which happens to be in row number 3. It is 166. And then if we combine them together, what we end up with, and this is the output that will be produced by this sequence of piping the population into group by and then piping that into summarise. This is the table that we're going to get. We're going to get a patch index, namely patch A and B, and then the maximum number of individuals in each of them. So notice that because we have grouped over the patches, we are no longer averaging over them. We're only averaging over days, and that is why the column patch is actually retained in the final dataset, and that makes perfect sense. We've made 2 groups. The 2 groups differ in which patch we're in, and in each patch we have computed a summary statistic, and the summary goes over day 1, 2, and 3. We just find the largest number, so the day column has been dropped. Just so that we see another equivalent example, let us see what happens if instead of computing the maximum number of individuals per each group, we calculate the mean number of individuals. And I don't think it will be any surprising. We do the exact same thing. We split up the dataset by group belonging, which in this case is defined by patch A or B. But then instead of picking out the maximum entry, we just take the arithmetic average of all the entries per group. So for the first group, the blue group, we take the individuals 66, 86, and 79 and take their arithmetic average, so it's going to be 70 something, probably. And then we take the green subtable, and there we calculate the average of 131, 102, and 166, which is going to be around 130. Let's see what the actual result is. Well, here we go. Again, in patch A, the average number of individuals is 77, and in patch B, it is 133. As a subsequent example, let us see what happens if instead of grouping by patch, we group by day, and otherwise do the same thing, we compute the average number of individuals. Well, if we group by day, then in fact, because there are 3 distinct days in the dataset, namely day 1, 2, and 3, there will be 3 groups instead of 2 in the grouped data. I've color-coded them, blue, green, and yellow this time. And then the summary statistic computation will be done on each of these 3 groups. So in other words, for the blue group, we're going to be averaging 66 and 131. In the green group, we're going to be averaging 86 and 102. And finally, in the yellow group, we're going to be averaging 79 and 166. And if we do that, we get the result where we have day as our first column, not patch, because those we've averaged over, so that is gone. But what we see is that on day 1, the mean number of individuals across the 2 patches was 98.5. On day 2, it was 94. And on day 3, it was 122.5. Okay, as a next step, let's see what happens if we group by more than one column. So in this case, we group the data by both day and patch. What happens then? The way to interpret this is that every combination of day and patch that is unique will define a unique group. So in this case, actually, all the 6 rows in this dataset will belong to a unique group because each of them are different, right? In the blue group, as you can see, we have day 1 patch A, and then in the green group, we have day 1 patch B. Then in the yellow group, we have day 2 patch A, in the gray group, day 2 patch B, and then in the pink group, day 3 patch A, and in the black group, day 3 patch B. None of those match with one another, and therefore each of them form their own group. Therefore, if we compute the mean over them, we just get back the exact same table that we started with because the arithmetic average of a single number is itself. But this didn't have to be the case. So imagine for one moment what would happen if, for example, the original pop table had another row, and the extra row would be in day 3 and in patch A. So for some reason, on the 3rd day of measurements, we made 2 distinct measurements in patch A. In that case, if we computed the summaries over that, those would be collapsed. And in the pink row, instead of getting back the previous 79, we get back the average of 79 and 43, which, as you can see on the right, is equal to 61. So the take home from this is that when we group data by multiple columns, then the only way that 2 rows will belong into the same group is if they match their values in all of the columns that we have specified. So in this particular example, they have to be identical in both day and patch at the same time. So at this point, let us go back to the group by function for just one moment, and let's see what it does. So as we've seen, when we group the data, it changes its structure internally, but it doesn't actually do anything visibly on the outside. Instead, when we group the data, what we modify is how subsequent functions will operate on the data. And we've seen that on the example of summarise. If we simply summarized without grouping the data, we got a different result than if we first grouped the data and then summarized. As it happens, this property is true for other functions as well, not just for summarise, and it will be useful to take a look at some examples. The first example is filter. So if we use it without grouping the data, then it does the usual thing. For example, if we want to filter for the number of individuals that is maximal, Then the way we do that is we specify a logical condition where we say ind, that is the entries in the column ind, should be equal to the maximum in that column. So because we're doing a logical comparison here, we're using the double equals symbol because that will return either true or false. And if we do that, we get back what we expect, the single row in the table that has the maximum number of individuals, which is 166 incidentally, and it is on day 3 and in patch B. Now, if we first group by patch and then filter for the maximum number of individuals, then this will be done for each of the groups, and the two groups here will be for patch A and patch B, and therefore actually the output will have two rows in it, namely the one for patch A and the other for patch B, and we can see that the largest number of individuals in patch A happened to have been measured in day 2, and it was 86 individuals, whereas the largest number of individuals in patch B was measured on day 3, and it was 166 individuals, the one that we've seen above. So similarly to the filter function, the mutate function is also another one whose behavior depends on whether the data are grouped. Again, as a simple example, let us mutate on an ungrouped dataset, and here we are creating a new column called mean ind, which simply takes the average of the number of individuals. Now you might be thinking, that's strange, that returns a single number, shouldn't that be a summary? No, it doesn't have to be. If it's used within mutate, then what happens is we compute that single number and copy that number over into every single row. And you can see that here in the output. So the average number of individuals across the data set happens to be 105. And then because we use mutate, that number is copied into every single row in these data. If instead we first group the data by day and then mutate on the mean number of individuals, then the output is different depending on which day we are at. Namely, for day 1, we only compute the average of number of individuals on that day, namely across patches A and B. So we get the average of 66 and 131. And that is 98.5, and that will be the result in both rows 1 and 2, namely those rows that belong to the same day. And then the same holds for day 2 and day 3. In day 2, the average is 94, and day 3, the average is 122. So as you can see, the behavior of the mutate function depends on whether it is acting on grouped data or not. One thing to note though is that the grouping information is retained after we finish mutating. And you can see that here in this little comment. You can see that the data are still grouped by day and that there are 3 different groups. Well, of course, day 1, 2, and 3, so those belong to different groups. In other words, after mutating, the grouping information doesn't go away, it's still there. And that is important to keep in mind because it can modify what subsequent operations do to the data. So for example, imagine that we pipe this dataset on into a filter function, and we want to filter for the row that has the largest number of individuals, that is, entries in the original ind column. And you might be thinking, naively, that doing so will return a table with just a single row, namely the one with the largest number of individuals in it, which is 166, and therefore we'll get back only row 6. But that is not the case, because the data are still grouped, and therefore we will get back a row for each of the groups, because the filter will still operate group-wise. So for this reason, one has to be aware of the fact that the grouping information is not removed just by performing some sort of operation such as mutate or such as filter on the grouped data. Now, just to make that a tad more confusing, the thing is the summarise function does not work in the same way. Namely, if we apply summarise to grouped data, then the grouping structure will change after that application. How will it change? I will not be going into the details of that because in my opinion it is simply not worth doing so. If you are interested in the details, you can always read up on it online or just check the help page of the summarise function within R itself. Just look at the .groups argument and its behavior and you can educate yourself on this. But here I will not be going into that. Instead, I'm going to teach you a workaround by showing you how you can remove grouping information from data once you are done computing on the groups. So the function that can do that is conveniently named ungroup, and all it does is it receives a table as its input, and it removes all the grouping information from that data. So for example, we could take our population data, group it by days, compute the mean number of individuals for each day, but then when we're done with that operation, then we ungroup our dataset. Similarly, if we would filter for the maximum number of individuals per each patch, so we first group our data by patch, then we filter for the maximum number of individuals in each patch, then unless we wish to do further operations on the dataset that is still grouped by patch, then we just pipe that into the ungroup function, and that will remove all the grouping. And the same holds for summarize. So if we want to compute the average number of individuals per patch, we do that, and after we're done with that, we just pipe that into ungroup. And again, that is safe. That means that from now on, there is certainly no grouping information in those data. So the general principle here is that every group by function should be paired up by an accompanying ungroup. So the pattern is always the same. We first group the data by something, then we perform some operation, or maybe multiple operations if we need to, but then after having done that, we always ungroup our data and return to a clean dataset without any grouping information. I should add that if you're watching this video because you are taking the course it comes with at Linköping University in Sweden, then I will make it a requirement that you ungroup your data once you are done with the grouped operations. So in other words, please make sure, whether it's in a quiz, whether it's in submitted assignments, that if you group your data and perform some operations on those groups, then after being done that, you clean up after yourself and always have an accompanying ungroup at the very end. So that was it for today. As usual, thank you for your attention, and I will see you in the next lesson.